So I'm Michael. I work at Apple on C++ debugging, and today I'm just going to talk about some cute improvements that we made to LLDB to make the life of people using LLDB slightly easier. So this talk was kind of teased in Konstantin's Sid Ranges talk last year, where he just showcased the thing that I'm going to talk about today. It's not really specific to Sid Ranges, but just motivated the work and catches people's attention. But it works with any kind of template that you're debugging. So this is going to be the running example. We're just declaring a STD map from integers to vectors of strings and taking a values view over that map, which just, so this LMs variable will just contain a view over all the values of that map. So if we were to print this in LLDB, this is what we used to see. This is not very useful. It has like a lot of visual noise in the type name and also doesn't really tell us anything about the range, the underlying range. So I'm just going to explain how we got from here to here. So before going into details, I just go over like a high-level overview of how type names get printed in LLDB. So what we first do when we print the variable is read the DebugInfo out of the object files, then create a Clang AST node for it, which David mentioned in his quick talk yesterday. Then we pass this AST node and all the related AST nodes to Clang, and then we ask the Clang type printer to actually print out that type name. If you want to know more details about how Clang's integrated into LLDB, Raphael's talk from a couple of years ago is a good reference. If we go back to this example, the first thing you'll notice is all these std basic string references, which we never actually specified in the source. So why are these printed if the type printer can actually omit these? So usually to debug these kind of things, we go to the Clang AST, which looks something like this, for example. And in the bottom, you'll see that there's this preferred name attribute, which creates the link between the std string and the std basic string instantiation. So Clang knows how to deal with it. And if we look at the type printer, there's this logic which takes the attribute, gets the type def it points to, and then just prints that instead. So why doesn't LLDB, why isn't that able to use it? So if we look at the AST that LLDB generates, you'll see that there is no preferred name attribute. So there's nothing Clang can do about that. So because LLDB creates the AST from dwarf, let's look at what that looks like. So there's a dwarf output, and here's the std vector value parameter that we pass to the map. And you'll see that the DebugInfo entry for that points to the std vector instantiation, and that template parameter just points to the basic string instantiation. So there's no link between the basic string and the std string. So LLDB can also not do anything about that. So what we did to fix that was simply add another level of indirection. We add this type def in between. So whenever Clang generates dwarf and sees that a type has a preferred name, it would just emit a pointer to that type def instead. And that just fixes all those problems in LLDB without actually making changes to LLDB. So this is what we're left with. So then there's still some stuff left, which is, in this case, the default template parameters, which we also never actually specified in the source, so are kind of useless. So why can't Clang deal with that? So if we look at the type printer, you'll see that there's this logic to check whether a template argument corresponds to a default template parameter and then drops it from being considered for type printing. So Clang can actually do it, but doesn't do it in this case. So if we dig into that substitutability check, you'll see that the template argument that it uses for this substitutability check, it gets from the template type parameter decal. And because that decal gets created in LLDB, let's have a look at what that looks like. So here you'll see the logic just creates this template parameter decal, but nowhere here do we actually set a default template argument. So why is that? Why can't we just do that? We'll just go back to dwarf. So here you'll see the std the allocator parameter, which is a defaulted template parameter. And if you have a close look at that, you'll see that the type of that in the DebugInfo is actually the std allocator instantiated with the vector directly. So there's no, so we lost all that generic information from the source. So from LLDB's perspective, it doesn't really know what kind of decal to create. Was the source actually instantiated with a vector, or was it dependent on a generic template parameter? So yeah, long story short, it's kind of hard to do with Dwarf. So we looked at the Dwarf spec, and Dwarf 5 actually specifies that there is this attribute that we can attach to a template parameter, which does exactly what we wanted, what gives us the information that we want to actually pass to Clang from LLDB. So we just made sure that with Dwarf 5, we actually emit this attribute in all the cases that we can. And as you'll see, when we compile with Dwarf 5, that attribute actually is on the comparator and the allocator. So then all we need to do is pass that info from Clang to LLDB back to Clang. So this is the Clang changes that we had to make. So here we steal a bit from the template argument type that encodes that information that a template argument is defaulted. When we parse the template specialization, we use that substitutability check that was originally a time printer. We do it in the parsing stage instead and set that bit on the template argument. Then the DebugInfo component, when generating Dwarf, can actually just emit this attribute whenever that bit is set. And then in LLDB, when we create the decal, we just read out Dwarf, set the bit, pass it to Clang, read the bit, omit the template argument. So so that's a lot of plumbing, but eventually it works out. And then we go from here to here, which gets rid of all the type name noise. But there's this one thing left, which is the underlying range isn't very descriptive. So then if we have a look at what this __ range actually is, that's in libc++, is really just a pointer to some underlying range. And because LLDB has the capability of formatting the children of a type with custom data formatters, that's kind of what we did. So here's a command to get the list of built-in data formatters for LLDB. And you'll see here's the entry for the ref view, which we had to implement for this. And it just matches the type name against that regex on the left and then invokes the corresponding data formatter. So here's like a brief implementation of it. It's really simple. It just reads out this range variable and then dereferences it, passes it back to LLDB. And then, it basically gives us all that info that we wanted. So that's pretty much it. Conclusion. LLDB makes heavy use of Clang for any sort of type info queries. And LLDB, the ASTs that it passes to Clang, it gets from Dwarf. It can also do it from other types of DebugInfo, but in this case, Dwarf. Improving debugging experience is kind of a balance, like where do you put the complexity, the compiler or the debugger? So you have to make those kind of trade-offs. It would be great if people kept debugging and LLDB in mind when developing language features or standard library features. And if you have any suggestions or changes that you want to make, open them on GitHub and we'll take a look. And that's it.